Here's a mechanics question which you might get as a first-year engineering student, or you might even get as a high school student. And this deals with the idea of friction, and it's somewhat tricky because the question doesn't tell you what kind of friction you're dealing with, so you have to find a way to figure it out for yourself, and we're going to look at how exactly to do that. And if you'd like to see anything similar to this on the channel, or if you have any particular questions that you'd like me to solve, let me know in the comments. So for this question, we're given a couple of things. So we know the masses of the two objects. So we know that the first object, object A or block A, but I'm just going to call it M1, this is equal to 20 kilograms, and then M2 is 100 kilograms. And then we know that the coefficients of friction of both static and kinetic friction between the two blocks, they're both equal to 0.5. So I'm just going to call this mu is equal to 0.5. And we have to find the acceleration of each part. So we have to find the acceleration of each block in two separate cases. So the first case is when the force that you're pulling that string is 60 newtons, and in the second case you're pulling with a lower force of 40 newtons. So let's deal with part A and let's see what we can do. So the first thing to do, or the safest thing to do in this case, as usual, would be to just draw the free body diagram of each object. So I'm going to start with block A, and I'm going to draw block A by itself. And then I'm going to draw, obviously, the forces acting on block A. So we know that that string is being pulled with a force P. And that force P, because it's acting directly on the string, that is actually the same as the tension in the string itself. So if you have this wheel here, which is kind of attached to the object A, then what happens is this part of the string is being pulled with a force P, but as the string goes around that small pulley, there is the same tension acting here as well. So even though you're acting on the string with a force P, the force that's acting on that first object is 2 times P, right? So I'm just gonna remove all the stuff from here just to simplify the drawing slightly, and then I'm just gonna draw a force of 2P acting on this first object, like that. And then there's also the weight, which is M1 times G. Then we also have this normal reaction force, which is N1. And then we have friction, right? So we have friction acting here, and I'm going to call this friction just FF1, or actually just call it FF, right? Because there's no reason to give it a subscript, because it's the same friction that will act on the second object. So this is block A, and then for block B we have this situation where this is block B, and then we have exactly the same frictional force acting on block B, because this is action and reaction. So if this force is acting on block A by block B, then this force is acting on block B by block A. So it's equal and opposite, equal in magnitude and opposite in direction. And then we have, again, the weight, which is M2G. We have N1 as well. So we have N1 acting down, because, again, this is another case of action and reaction, or the other way around, depending on how you want to look at it. And then we have another normal reaction force here from the ground acting on block B. And that's it. So the objects are also accelerating, so they could have the same acceleration if they move together, or they could have different accelerations if they're not moving together. So I'm going to say this has an acceleration A1, and this has an acceleration A2. Okay, so let's write Newton's second law for each object. So for the first one, we have that in the x direction, and I'm just going to look in the x direction, we have that 2p minus friction is equal to m1 times a1, and then for the second object there's only one force acting, which is the friction. So friction is equal to m2 times a2. Okay, so this is one of those, I think, moments that are, or one of those ideas that are counterintuitive for some students, because while this friction is opposing the motion of the first object, that sort of makes sense, the same friction is accelerating the second object underneath. It's accelerating block B, which some people find this to be a weird concept, because friction, we're used to thinking of friction as something that's always opposing the motion, but there are many cases when friction helps you move, when friction accelerates an object. So one simple example is walking, right? If there's no friction, nobody could walk or start their car or drive their car or anything like that. So in any case, those are the two equations that we have. And if you look at them closely, you should realize that we can't actually solve them because we have too many unknowns. We have the friction, we have the acceleration of block A and the acceleration of block B. So we have three unknowns in two equations. And then we have to think about what can we actually do about this situation. So there are two cases that can occur. So case one is when the two objects move together, and the second case is when the two objects move separately. So let's try to understand when each case occurs. So essentially this first case, so case one, occurs if the two objects are not sliding relative to each other. So if they're not sliding relative to each other. So in this case, the type of friction that we would be dealing with, is static friction, right? Because static friction, by definition, doesn't involve any sliding between the two corresponding surfaces. And in case two, we have the opposite situation. So in case two, the two objects are sliding. Relative to each other. Now, in this second case, so if we actually are in the second case, we actually know what the friction is. So if we're in the second case, the friction is actually equal to mu times n1, right? So we know that when there is kinetic friction between two surfaces, the friction is equal to this friction coefficient multiplied by this normal reaction force n1, right? So, and we can actually find how much that is. So the friction is mu times n1, but n1 and the weight are the same in this case because there's no vertical acceleration. So that's m1 times g. So that's 0.5 multiplied by 20 multiplied by 9.81. So we've got 0.5 times 20, which is 10, times this. So this should be 98.1 newtons. So if our friction turns out to be less than this value, and by the way, this is the maximum value the friction can get, right? But if the friction, so this would be sort of FF max, if the actual friction value is less than this, then we have static friction. So how do we do this? Well, let's assume, and this is a valid way of doing this question, let's assume we are in case 1. So assume case 1 to be true. So if case 1 is true, what it means is that the two objects are moving as one, which means we have static friction. So we have static friction, and the static friction would need to have a value less than 98.1 newtons. And if they're moving together, then the accelerations of the two objects are the same, and I'm going to call them equal to this value of A. Okay, so let's rewrite those two equations here for case 1, right? So we have that 2p minus the friction is equal to m1 times A, and I think the other one was ff is m2 times A. Right, so what we can do is we could divide one by the other, but I'll just add them up to cancel the friction force and find the acceleration first. So we have 2p is equal to m1 plus m2 times A. So the acceleration is 2p over m1 plus m2. 2 times p is, I believe, 2 times 60, which is 120. And then m1 plus m2 is also 120. So this would be 1 meter per second squared. So this would be the acceleration if the two objects are moving together. But the critical point is checking how much the friction actually is. So the friction is m2 times A. So m2 is 100. The acceleration is 1. We just found it. So that's 100 newtons. This is the static friction, but it turns out this is actually greater than the maximum allowable value of friction, which is absurd. So we've reached a contradiction, which means that case 1 is not actually valid. So case 1 is not valid. And it's not valid because for this case to be valid, the amount of friction you need is 100, which is greater than the maximum value the friction can actually be, which is 98.1. So we're not in case 1, we are in case 2. So in case 2, remember the two objects are moving separately. So they're moving separately. And if they're moving separately, we know that the accelerations will be different. But we also know that the friction is going to have the maximum value, which is mu times n1, which is 98.1 newtons. And now it's relatively straightforward to actually find the two accelerations. So we have the first equation was 2p minus mu n1 is equal to m1 a1, and then we have mu n1 is m2 a2. So we'll end up with two different accelerations, and I think we can do a2 first because it's a bit more straightforward. So this is mu n1 over m2, which is mu m1g over m2, and that's the acceleration of the second object, which is 0.5 times 20 over 100 times 9.81. So this is, let's see, 0.5 times 20 by 100 times 9.81. So this is 0.981 meters per second squared. It's the acceleration of the second object. And the acceleration of the first object, you can get it from here. So that's a1 over 2p by m1 minus mu m1g over m1. So as you can see, the m1s cancel in this term, and then this is 2 multiplied by 2 times p, which is 120 over m1, which is 20, minus 0.5 times 9.81, which should be, so 120 over 20 is 6, minus half of 9.81 is 4.905, and the result is 1.095 meters per second squared. And that's the answer for part A. Okay, so hopefully that makes sense. And then for part B, the only difference between part A and part B is the pulling force. So in part B, I think you're pulling with a force of 40 newtons according to the question, and you're pulling the string with a force of 40 newtons. So actually what happens is that this object, this first object, block A, how we call it, this is being pulled with a force of 80 newtons, like this. And again, we have to figure out in which case we're in. So is this going to be static friction? Is it going to be kinetic friction? Are the two objects moving together or not? So thankfully, in this case, it's easier to figure out, and this is how you do it. So you've got your weight, you've got your normal reaction force N1, and of course you have your friction. And I can tell you straight away, without doing many calculations, that this is going to be static friction. And here's why. So the maximum value of friction that we can have is when the two objects are sliding relative to each other, and that friction is going to be 98.1 newtons, right? So if this friction is kinetic, in other words, if this is 98.1 newtons, that's a contradiction, because it's like you're pulling the block with a force of 80 newtons, but this force is higher, so it's going to move to the left, which makes zero sense whatsoever, if you think about it. Which means this force is not only less than 98.1 newtons, it's less than 80. So I'm gonna remove this nonsense. So this force will be less than 80 newtons, which is less than the maximum allowable friction force, which means that we're in the static case. So the two objects will actually move together. So we are in, I think this was case 1. The two objects move together, which means they have the same acceleration, and the friction force is strictly less than mu n. It's actually strictly less than 80 newtons as well. Yeah, or it could be 80 newtons as well, I think. But it's strictly less than the maximum value, which is 98.1 newtons. Okay, so what we can do in that case is we rewrite the two equations from above. One of them is this one, and this is m1a, right? Because we're using the same acceleration for both objects, and this is m2 times a, and then, you know, we don't care about what the friction is. We can find out if we want, but if we add up, we should get 2p is equal to m1 plus m2 times a, and then the acceleration is 2p, which is 80 over the two masses added up, which is 120. So this is 8 over 12. I think we can simplify by 4. So this is 3. This is 2 over 3, which is approximately 0.67 meters per second squared. So that's the acceleration. And while we're at it, I guess we can find the friction as well as an added bonus. So the friction is going to be, I'll use this equation because it's quicker. So it's 100, which is the mass of the second object, times 0.67, and this is going to be, I guess, approximately 67 newtons. So you can see that it's less than 80 and clearly less than this maximum value. And that's how I would solve this question. So it's quite involved, but that's the framework for even more complicated situations. And maybe next time I'll have a look at a few more examples involving friction that are even more complex than this. So until then, that's the end of the question.